We are now ready to start looking at cyclohexane molecules that have substituents on them. So we have a couple of examples of di-substituted cyclohexanes that have di-substituted means that they have two substituents attached to the ring. And our task here is to draw the most stable conformation for these molecules. So before we jump into that, when you are being asked to draw a conformation of cyclohexane, that is your chemistry instructor's way of hinting to you that you need to draw cyclohexane in its chair conformation. You cannot use line notation to represent a stable or any type of conformation at all. So when you see the words draw the most stable conformation, you have to draw a chair. And when you are drawing the chair conformation of a cyclohexane that has substituents on it, like this first one right here, you are going to have to think about how to orient or position the substituents that are on that cyclohexane. So first thing that we're going to tackle before we get into drawing this is interpreting the wedge and dash notation that's being used on these molecules. So the first one that we're looking at has one methyl group on the wedge and the other methyl group on the dash. And so what that is telling us when we're looking at the wedge or dash notation is that it's telling us the position of these substituents relative to the plane of the ring. For me personally, I always interpret the wedged substituent to be above the plane of the ring and the dash substituent to be below the plane of the ring. But that is not, there's no standard for that. The wedge could just as well be below the ring and the dash could be above the ring. You might be wondering, what exactly does she mean when she's talking about above and below the ring? So if you have a model, we're going to look at a mole view model. When you turn this molecule so that the ring is flat, and you know from experience that cyclohexane really doesn't flatten out, so it's going to have kind of a zigzag shape. And you're looking at it from the side, substituents are either going to be sticking up or they're going to be sticking down. And that's what this above the ring, below the ring refers to. So let's look at a mole view model of this particular di-substituted cyclohexane. Now in the mole view model, just to give you a heads up, it's going to have the methyl groups on the sides, the left side and the right side, rather than up and down. And I've oriented it this way because it will make it a little bit easier to see what is already going to be pretty difficult to see. What you're going to be looking for when we look at this mole view model is the position of the methyl groups and whether the methyl groups are on bonds that are pointing up or pointing down. So let's go take a look at that. So here is the mole view model, and this would be if we're looking straight down on it, and we've got the methyl groups on the left side and the right side of the ring. And so what I'm going to do is turn this model so that we're going to get the cyclohexane, the six-membered ring, as flat as possible. It doesn't flatten itself out as we've talked about. And as we flatten it out, you will see that the methyl that's on the left-hand side is in the equatorial down position for this particular molecule. And the methyl that's on the right-hand side is in the equatorial up position for this particular model. So the wedge and the dash are indicating that one substituent is on an up bond and one substituent is on a down bond. So how are we going to draw that in terms of being able to represent the most stable conformation? So first of all, we already know that this means that we have to draw a chair conformation. And when I draw a chair conformation, I will always go around the ring and fill in the template for the substituents that are on all of the carbon atoms. So I just did my axial bonds first, alternating up and down around the ring. And now I'm going to go back and fill in my equatorial bonds, alternating down and then up, down, and then up. So every single carbon in the ring has one axial bond and one equatorial bond, and also every carbon has one bond sticking up and one bond sticking down. So it's time for us to fill the two methyl groups in, and we can put them anywhere we want. Like we get to choose, let's say that this is our carbon number 1. We get to choose on this ring which one we want to make carbon number 1. Let's say that this guy right here is our carbon number 1. And because this methyl group is on a wedge, and I like to interpret the wedge as being above the ring, which I am always personally indicating as being an up bond. So that means that I have a methyl group on carbon number 1 in the up position, like that. And the other substituent on that carbon number 1 is a hydrogen, which we don't need to represent. So I'm going to erase the line that I drew for that bond to hydrogen. So now let's continue around the ring. Carbons 2 and 3 only have hydrogens on them. And so I'm not going to draw them on this molecule, so I'm just going to erase those bonds. And I am now ready for carbon number 4. Carbon number 4 has a methyl group, and this methyl group is on a dashed bond, which I prefer to think of as being below the ring. And below the ring, to me, is always drawn in the down position. So we are at carbon number 4. We have to add a methyl group, and we have to add that methyl group to the down position. The other substituent on carbon number 4 is a hydrogen, and carbon number 5 and 6 also have hydrogens on them, so I'm going to erase those bonds. I don't need them anymore. I drew them in because they help me make sure that I'm getting my substituents pointing in the right direction, and also drawing them equatorial or axial, whichever is correct. But here they are. So here is a conformation of this particular molecule. The question is it the most stable conformation, or is there one that's better? And in order for us to answer that question, we have to draw a ring flip of this molecule. So remember, in the ring flip, we are taking this carbon right here and pushing it up. We're taking this carbon right here and pushing it down. So we are changing the conformation. It's still going to be a chair. It's just going to be oriented in a different direction. And we took carbon number 1 and pushed it down. So carbon number 1 is now down here. This is 2, 3, 4, 5, and 6. Now remember, when we do a ring flip, our substituents change, the positions change a little bit, and we talked about how up stays up. So this substituent is going to stay up, but it changes from axial to equatorial. So this methyl group on carbon number 1 is going to stay up, but instead of being up axial, it's going to be up equatorial. And for carbon number 4, when we do a ring flip, down stays down, but axial becomes equatorial. So now carbon number 4 has its methyl group down, and it's down equatorial. So it's going to look like this. And so these are the two conformations of cyclohexane. Which one is the most stable? That's the question. Which one is the most stable? So if you actually built this model and you put these methyl groups in the axial position, you would see that they are pretty jammed up with the hydrogens that are also in axial positions on this molecule. So I'm going to draw just the hydrogens into this molecule, and there is going to be quite a bit of steric hindrance between these methyl groups Don't forget that those hydrogens do spread out. So there's going to be quite a bit of steric hindrance between the methyl groups and the hydrogens that are on the same side of the ring. And that is true whenever our substituents are in the axial position. When they're in the equatorial position, because they are away from those axial spots, if we can go back to mole view and look, we don't see steric hindrance in this situation because the methyl groups are out on the side and they're not interacting with the hydrogens that are attached to the carbons of the ring. So the most stable substituent, structure, conformation, is the one where our substituents are in the equatorial position. And this is going to be a rule of thumb that we'll summarize at the end of this video. In general, we want to be able to put as many substituents as possible in the equatorial position because that gives them the most amount of space. That's where they are the most stable. Let's practice with another example. So again, we're going to be drawing the most stable conformation, which means right off the bat, we know that we're going to need to draw a chair conformation. That's a really bad looking chair. And as I said, I always like to start by drawing in my bonds or a template for my bonds because I don't ever want to worry about mixing up. Is it supposed to be up? Is it supposed to be axial? Is it supposed to be equatorial? Whatever. So now I get to choose where do I want to start drawing this molecule. Let's stick with the same format that we had in the example above. So we're going to call this guy carbon number 1. That would not be appropriate if we were naming it for IUPAC, but for the purposes of keeping track of carbons, this will work. And we're going to make this guy carbon number 1 of our chair conformation. So again, I like to interpret the wedge as being above the ring or up. So that means on carbon number 1, I want to put the methyl group sticking up in the up position, and then I will go ahead and erase the other spot on that carbon. And now let's do carbon number 2. That's this guy right here. Here's a new abbreviation that we haven't seen before. The abbreviation ET is just shorthand for ethyl. We also have ME for methyl. Those are used pretty commonly. PR for propyl, not used quite as much. So we have ET, or an ethyl group, that's on carbon number 2, and it is on the wedge, which I always interpret to be above the ring or sticking up. So that means our ethyl group is going to be right here, right there, sticking up, and we do not need any of the other substituents positions on the ring. So I'm just going to get rid of all of them like that. And now we need to ring flip it. So we're going to take this carbon right here and move it up. We're going to take this carbon right here and move it down. And we will draw the ring flipped. So when we do this ring flip, carbon number 1 moves down and is now in this position right here. So here's our carbon number 1, and this is going to be carbon number 2. And when we do the ring flip, remember up stays up. So our methyl group stays sticking up, but axial becomes equatorial. So now carbon number 1, the methyl group is up equatorial. And for carbon number 2, up stays up, but equatorial is going to become axial. So we'll squeeze that guy in. So now we have to compare and decide which of these two is the most stable. Remember, in the previous example, we talked about put as many substituents as possible into the equatorial position. So this conformation has one equatorial substituent, one axial. This conformation has one equatorial, one axial. So in that regard, it's a tie. When you have this type of situation, what you're looking for is putting the biggest or bulkiest substituent into the equatorial position where it will have the most space. So this one is the most stable because the big ethyl group is equatorial where it has the most space. And let's add that note up above. The first example we did was most stable because in this conformation, both of these substituents are in the equatorial position. Okay, so now let's look at one more example. Now this particular cyclohexane has got 4 substituents on it. And again, our job is going to be to draw the most stable conformation. Now this time we're going to do this a little bit faster. So we're going to try to avoid having to draw the ring flip. We're going to try to get it right on the first try. And let's go ahead and let's fill in our bonds: up, down, up, down, up, down, down, up, down, up, down, up. And let's number these carbons: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we've already learned that when we are looking for the most stable conformation, we've already talked about how the best position to put substituents is in the equatorial position because that's where they have the most room. And also we've learned that we want to put the biggest substituent in the equatorial position. In case the terminology is getting overwhelming, the equatorial positions are the ones that are angled up or angled down. So we want, our number one priority is to find the biggest substituent and put it in the equatorial position. And on this molecule, the biggest substituent is the tert-butyl group. It has 4 carbons, and 3 of those carbons each have 3 hydrogens, so this is definitely the biggest substituent out of all of them. And we want this big giant substituent to be in the equatorial position. Now I put the tert-butyl group on carbon number 3 when I numbered it, and over here on carbon number 3, I want my tert-butyl group to be in the equatorial position. However, this is a little bit inconsistent with how I like to think about these things because I like the wedge. I always like the wedge to be up, sticking up. And on carbon number 3, my equatorial spot is sticking down. And because I'm a creature of habit, I'm actually just going to redraw and renumber my cyclohexane chair conformation completely. Up, down, up, down, up, down, down, up, down, up, down, up. So I want my cyclohexane to be up and equatorial. Up because it is on a wedge, and equatorial because it is big. It's the biggest substituent out of all of the ones in this particular molecule. So I am going to choose to put it, I want to put it on any one of the carbons that has an up equatorial spot. And I like the look of this guy right here. So I am going to put my tert-butyl group right here, up and equatorial, which means that this guy is going to be carbon number 3. And this will be 4, 5, 6, 1, and 2. So I just made that decision based on where I wanted to start drawing the tert-butyl group. So now what's going on as we go around the ring? Our next carbon, carbon number 4, has only hydrogens on it. So that means I can erase these reference points that I've drawn. And now we're moving on to carbon number 5. Carbon number 5 has a chlorine on the dash, which I always interpret as the down position. So on carbon number 5, I need to draw my chlorine on the down bond. And that is going to put it into the axial spot, but that's okay. The position of the chlorine doesn't matter. What matters is the position of the tert-butyl group. That one has got to be equatorial because it is so big, and because chlorine is dash while tert-butyl is wedge, these two substituents have to be pointing in different directions. One is up, one is down. So moving on, carbon number 6 has nothing on it, so I'm going to erase those reference bonds as well. Carbon number 1 has a methyl group, and that methyl group is on the dash, which I interpret to be down. So on carbon number 1, I'm going to draw the methyl on the down bond, which is also an axial bond. And we'll go ahead and erase that line right there. And then last but not least, we have carbon number 2. This has an isopropyl group on it. The isopropyl group is on a wedge, which I interpret to be up. So over here on carbon number 2, the up bond is the isopropyl right there. Nothing on the equatorial bond, so I'll erase that. And this is the most stable conformation of this molecule. Even though 3 of the substituents are in axial positions, that does not matter as much as putting the biggest substituent in the equatorial position. That's the most important thing, especially when you have a tert-butyl. That tert-butyl substituent can't go anywhere else. Tert-butyl only goes in the equatorial position.